All right, well, the good news is separable equations, we already did those, didn't we? What were separable equations?
Ones where you can get everything on one side and everything on the other side.
Ones where you could get all the y's on one side and all the x's on the other side. The only difference here is what they're going to do. They're going to give us what are called initial conditions. So we might have something like y times x plus 1, or y times x plus 1, plus y prime equals 0. And then they give us what's known as an initial condition, y at negative 2 equals 1. We're going to solve just like we did. We're going to separate our variables and we'll integrate. What's this initial condition going to do for us?
You can plug those values in for the y prime.
We'll plug these values in for the y and the x when we get all done, and what will that let us figure out?
C.
The c value. So that's the only difference. So it's kind of like the difference between a definite integral and an indefinite integral. With indefinite integrals, you finish with a plus c. Definite integrals, you end up with a number. That's what these initial conditions are for. They're going to allow us to get rid of the plus c and write a number. All right. Tell me how to separate my variables. Subtract. So I'm going to write this as dy dx equals minus y times x plus 1.
You can't just plug it in as it is and find y prime.
No, because before I can integrate, I've got to have all the y's on one side, all the x's on the other. So how do I get all the y's on one side, all the x's on the other?
You multiply by dx and then divide by negative y.
Yes, that would work. I'm going to divide just by regular old y and keep the minus sign up there on top. But what you said would work. I'm going to write it as dy over y equals negative x minus 1 dx. I prefer to have a negative sign on top of something than on bottom. So I'm going to leave the negative sign there and just do it. Now I can integrate. Got all the x's on one side, all the y's on the other. Integration is very easy. ln y equals minus 1/2 x squared minus x plus c. And then we went through this process the other day of getting the y all by itself. What was our method for getting the y all by itself? E on both sides. So we would have y equals e to the negative 1/2 x squared minus x plus c. But then typically we rewrote that as e to the negative 1/2 x squared minus x times e to the c, where we use our property of exponents, where if we multiply things with the same base, that's the same as adding the exponents. And then we use some sloppy notation, and we called e to the c, c. It's a constant still, so we just renamed it c. So typically we wrote y equals c e to the negative 1/2 x squared minus x. So there's all the work we did the other day. The only new thing now is we plug in this initial condition and we figure out the c number. So I plug 1 in for y. I plug negative 2 in for x. I'm going to have 1 equals c e to the negative 1/2. When I plug in negative 2, that's 4. So negative 1/2 times 4 is negative 2 minus negative 2. Negative 2 minus negative 2 is 0. E to the 0 is 1. So that's just c times 1, which is c. So c is the number 1. So final answer. Y equals e to the negative 1/2 x squared minus x. So not much new there. The only new thing is, after you solve, plug in your numbers and figure out the value c.
When we start right plus 1 if c is 1, that would be...
Well, c is 1, so I'm going to have 1 times
Oh, okay.
that thing. Yeah. So it looks a little confusing because c was written as a plus up there. But then this c here really isn't the same number as that c right there. That's, again, sloppy notation, but that's the standard thing that we do. Call it c over and over and over. Other questions?
If you were to substitute in the 1 and the -2 before we brought it down to CE to -1/2 x squared minus x. If you had done it when it was still e to the whole thing, would you still get the same answer?
Excellent question. His question is, if I had left it this way, y equals e to the -1/2 x squared minus x plus c, and I plugged in my initial conditions, would I get a different answer? Let's find out. Plug 1 in for y. Plug -2 in for x. So again, I'm going to have -1/2 times 4, that's -2, minus -2 plus c. So that's going to be 1 equals e to the c. So in this case, c would have to be what number? And the natural log of 1 is a nice number. It's also called 0, right? C would have to be 0. E to the 0 gives me the number 1. So in this case, my value for c would be 0, which is a different answer that I got from here for this c. But look what happens if I take the 0 and plug it in right there. That part disappears, and I do get exactly the same answer. So the value of c is different, but the final answer that you get is really exactly the same. Other questions?
So could you do that if it wasn't equal to, you were plugging in -2?
What do you mean if I weren't plugging in -2?
So like y of -3 equals 1, or if it was a different number and it didn't work out, so 1 equals.
So you're suspicious of the fact that when I plugged in -2, I always got the answer 0.
Yeah.
All right, so let's try that. I don't know. So we had y equals, our solution was y equals e c times e to the -1/2 x squared minus x, or it was e to the -1/2 x squared minus x plus c. And you want to start with a different initial condition like -3 comma 1. And does it matter which form I write it in? Will I still get the same answer? I don't know. No, I do know, but we'll work it out anyway. Plug in 1. I get 1 equals c e to the -9/2 plus 3. Because -3 squared is 9. 9 times a half is 9/2. Minus a minus is plus 3. What's -9/2 plus 3? -9/2 plus 6/2, 3/2. So this is c e to the -3/2. Okay, so now how do I get the c all by itself here? Divide by e to that quantity, or conversely, I could multiply by e to the 3/2. Because when I multiply these together, I would add my exponents and they would add up to 0. E to the 0 is 1. So we get c equals e to the 3/2 there. Which means our solution would be y equals e to the 3/2 times e to the -1/2 x squared minus x. Now let's try it if we're written in this form. We would have 1 equals e to the -9/2 plus 3 plus c. That would be the same as 1 equals e to the -3/2 plus c. So what number would c have to be there to make that work? Positive 3/2, because I would need -3/2 plus 3/2 to get 0. E to the 0 would give me 1. So again, I get a very different e number, or a very different c number. In this case, c has to be 3/2. And then I would write my answer as e to the -1/2 x squared minus x plus 3/2. But is that the same answer? Yeah, because I could do the same trick where I just take this part and peel it off and write it as a multiplication. So it really doesn't matter what your initial conditions are. It doesn't matter which form you write it in. It's just typically we prefer it in this form because in this form, this value of C had an important meaning for us. C was like our initial population, our initial amount of material that we started with radioactive decay, or maybe our initial investment if we were dealing with money. So typically we prefer it in this form because that number C tells us something important, where this number C doesn't have a whole lot of meaning to it. Okay, other questions? All right, the other thing we have in this section are what are called homogeneous equations. And what I heard is the word homogeneous you're familiar with from science. And you told me, what does the word homogeneous mean in science?
All things in the set are the same type.
All things in the set are the same type. In mathematics, homogeneous means all terms have the same degree. So we have a bunch of things that are all of the same type. They all have exactly the same degree. So a homogeneous equation might look like this. X cubed plus y cubed dx minus x y squared dy equals 0. All right, the first thing I want to tell you about this equation is it is not separable. You can try all you want. I promise you, you are not going to be able to separate the variables. So we can't solve it the way we solve it. Now, this equation is homogeneous because every term is degree 3. And some of these are easy. What's the degree of this term? 3, because it's got an x cubed. What's the degree of this term? 3, because it's got an x cubed. What's the degree of this term? 3, because the rule is when you have mixed variables, what do you do with the exponents? You add them. This one has degree 1, this one has degree 2. You add them, that's degree 3. So that's how you identify a homogeneous equation. You identify a homogeneous equation by looking at the exponents and making sure that all the exponents are the same. This is degree 3, that's degree 3, that's degree 3.
Is it any case that you have something like that with 3 degrees and each one's non-separable for anything?
It is possible that all of these could be degree 3 and it could also be separable. Yes, that can happen. So equations can be more than one type. They can be separable and homogeneous at the same time.
How is it again that the x, y squared is of the third degree?
When you have mixed variables in a term, you add the exponents. So the x has a degree 1, the y has a degree 2, 1 plus 2 is 3.
I was just thinking this is we're coming up on like stuff like that in physics, and it'd be nice to know that there's no answer before you work all the way through it, you know what I mean? That it's non-separable.
Right. So this one is non-separable, but that doesn't mean there's no answer. It means we have to solve it a different way. And that's what we're going to learn today. So, we identified it as homogeneous because all the terms had degree 3. Once you identify it as homogeneous, you're going to make a substitution. You're going to let y equal v times x. Where we're thinking of v as being some function. V is not just a number. V is a function. We don't know what the function is. It turns out it's not going to matter. So I'm going to need to plug in for y. Wherever I see a y, I'm going to need to plug this in. But I could divide here by dx. And so I've got a dy dx, which is a derivative. So I'm going to need to plug in for y prime also. So I've got to take the derivative. Y prime is, what's the derivative of v times x? And remember, v is a function. V is not just a number.
1D.
If v is a function, then what rule do you have to use? chain rule and product rule because we have multiplication right there. So I'm going to leave the first one alone. That's v. Take the derivative of the second one. The derivative of x is 1. Plus, I'm going to leave x alone, and I'm going to take the derivative of v. What's the derivative of v?
V times v prime.
Well, you're close. The derivative of v is just v prime. There's no v times v prime. There's just v prime. All right, so I'm going to rewrite this equation. This is x cubed plus y cubed minus x y squared y prime equals 0. So I divided by the dx, and dy over dx I simply wrote as y prime. So I'm going to make two substitutions. Everywhere I see the letter y, I'm going to plug in vx, and everywhere I see y prime, I'm going to plug in v plus x v prime.
Wait, did you, like, divide and then move the x back over?
All I did is I divided by the dx right there. And I did it in all three places. And then I chose to write dy dx as y prime just to make it match this.
Okay, so we don't have to, like, add dx like on both sides?
Nope. Nope. I could have if I wanted to, but I chose not to. Okay, so we make our substitutions. This is an x cubed plus vx whole thing cubed minus x times vx squared times v plus x v prime equals 0. And it looks like we made it worse, doesn't it? Well, it's about to get better. All right, so here's what's going to happen. Remember when we started, we looked at all the terms, and we said all the terms were degree 3? After you make this substitution, what's always going to happen is every term should have an x cubed. Since each one began with power 3, after you make these substitutions, everything should have an x cubed in it. Does everything have an x cubed in it? I got an x cubed there. I got an x cubed there. X squared times x is x cubed there. I got x cubed everywhere, don't I? So what can I do with x cubed? I can divide by it. I can factor it out and divide by it. So I divide everything by x cubed. I have 1 plus v cubed minus v times v plus x v prime equals 0.
Is that the v squared?
V squared, absolutely, thank you. V squared right there. If I have done everything correctly, this new equation that I have will be separable. So at this point, I should be able to get all the v's on one side and get all the x's on the other. So I got to do a bunch of algebra here. Any suggestions on how to get all the v's on one side and get all the x's on the other? Distribute the v squared, all right. 1 plus v cubed minus v cubed, hey, that looks handy, minus x v squared. And I'm going to go ahead and write this as dv dx. Since I'm going to try to separate my variables, I might as well write that as dv dx because I'm going to have to get all the v's on one side, all the x's on the other. And I was saying this is handy because the x cubes go away. Or the v cubes, I mean, those go away, like that. Now what?
Subtract 1 divided by x.
Subtract 1, all right.
By negative x.
So negative x v squared dv dx equals negative 1. And then I like what you said. You said divide by negative x, multiply by dx, And things will be separated, won't they? So I'm going to have v squared dv equals 1 over x dx. I'm able to separate my variables. All right, that was the hard work. Now comes the easy stuff. Hard stuff in math problems is always the algebra. The easy stuff is calculus. We have to integrate. What's the integral of v squared? Oh, that's a dv right there, by the way, not a dx. The integral of v squared is 1/3 v cubed equals the integral of 1 over x is
Natural log absolute value of x plus c.
natural log absolute value of x plus c.
It's just a big cube right there, not big square.
And that's a v cubed right there. Certainly is. I'm almost done. The last thing I need to do, my original equation started with x's and y's. So my final answer should end with x's and y's. So v is y over x. So I'm going to write this as 1/3 y over x cubed equals ln absolute value of x plus c. And that's a perfectly acceptable answer, but if we were to look up the answer in the back of the book, my guess is they would write it as y cubed equals 3x cubed ln absolute value of x plus 3cx cubed. So what did I do to go from there to that last step? I multiplied by 3x cubed to get rid of those two little fractions right there. If you were doing this problem on a quiz or on a test and you left your answer just like that, that's going to be perfectly acceptable by me. But like I said, my guess is the back of the book would probably write it that way.
Is there a shortcut?
Not that I'm aware of, other than type it into Wolfram Alpha.
This doesn't happen with why are we doing it?
Yeah, what can that be used for?
What is this used for? Well, unfortunately, this isn't a full course in differential equations, so we don't really answer that question. But when you take differential equations a year from now, we will model different phenomena by differential equations, and then we'll solve. For today, for example, today what we did in differential equations is we had a weight on a spring, and we had the spring bounce up and down, and we found the equations that match that spring motion.
Wait, so that's like, so is that just the spring, or is it like not, like have air and stuff around it?
It was a big thing, and I stretched it, and I let it go, and it bounced up and down, and we figured out the equation.
Was it in a frictionless vacuum?
No,
Okay, that's what I was wondering.
it was not in a frictionless vacuum. It was right in the classroom. If it were in a frictionless vacuum, the answer would be very easy. What kind of graph would you get if it were in a frictionless vacuum? You'd get exactly a sine curve. But we were not in a frictionless vacuum. So we take into account gravity and friction and the spring constant and all that stuff, and we actually come up with the equation. So that's what you have to look forward to. For today, you're just solving. You're just going to manipulate some symbols. All right, let's do one more of those. How about x squared plus y squared equals 2xy dy dx. So my first question to you is that equation separable?
Yes.
I heard a vote for yes, a vote for no. Somebody's right, somebody's wrong.
You can use the same rule we just did, can't you?
Well, it is homogeneous, but my question was, is it separable?
I don't think it is, because the dx squared plus the x squared.
I don't think it's separable either. The way it's, in order to be separable, the powers on the y's have to match. That's how you can usually tell real quickly if an equation is separable or not. The powers on the y's have to match. They don't. So this is not separable. Would be my guess. You can try it. My guess is you won't be able to separate your variables. Is it homogeneous? Yes, because this is power 2, that's power 2, and that's power 1 plus 1, which is 2. So it is homogeneous. And again, next spring, when you take differential equations, you will learn that this equation also happens to be something called Bernoulli. And so when you take differential equations, you'll have two options of how you can solve it. You can solve it as homogeneous or Bernoulli, whatever Bernoulli means. Something more to look forward to. But the important thing for us is we recognize it's homogeneous. So we know to make the substitution y equals vx. We take the derivative, dy dx is v plus x dv dx.
Well, y always equal vx.
Y will always, always, always equal vx for homogeneous equations. Absolutely. If you were solving it as a Bernoulli equation, y would be something else. But you don't have to worry about that today. So for you, y will always be vx. All right, so we make our substitutions. X squared plus vx squared equals 2 times x times vx times v plus x dv dx. Once again, at this point, two things should happen. The first thing that should happen is you should be able to reduce x squared out of everything. This time it's x squared because everything started power 2. After you divide everything by x squared, the equation will be separable. So those are the two things you're looking for. Do I have an x squared everywhere? Got one there, got one there, got one there. 1 plus v squared equals 2v times v plus x dv dx. And now I just have to work through the algebra and separate my variables. Multiply the 2v through. 1 plus v squared is 2v squared plus 2vx dv dx. Subtract 2v squared. 1 minus v squared equals 2vx dv dx. And now I think I'm ready to separate. How am I going to separate? That would work, dividing by 2v, except if you're going to divide by 2v, then you're going to have to divide by dv also. You'd have the dv on bottom, you'd have the dx on bottom. We need the dv and the dx to be on top.
So you divide by 2x, multiply by dx, and subtract, or add these.
Absolutely. I'm going to multiply by dx to get the dx on top. I'm going to divide by just x. You said 2x. I'm going to divide by just the x. And then I'm going to divide by this 1 minus v squared. Doing all that, I multiply by the dx. That gives me a dx on top. Divide by that x. That's an x on bottom. Equals 2v. I'm going to divide by the 1 minus v squared. And then dv. It would not be wrong at all to divide by the 2x. I chose to divide just by the x because I wanted dx over x, because it's easy to integrate dx over x. I don't need to use a u substitution or anything. What's the integral of dx over x? ln x. So this is going to be ln absolute value of x plus c equals, how do you integrate the right hand side? U equals the bottom. U equals 1 minus v squared. So 2u is minus 2v dv. And that's another convenient reason for leaving that 2 on top, as it happens to work well with the u substitution. But we do need to sneak in a minus sign. So we need two minus signs. So we're going to end up with minus integral 1 over u du. Okay, so all we got to do now is integrate and then a whole bunch of back substitution and we're all done. Ln absolute value of x plus c equals minus ln of u, but that's minus ln of 1 minus v squared.
Again, there'd be a C over there, but there's a matter.
Correct, there would technically be a c on both sides, but we don't care. We only need one of them because we would combine our c's. I got to eventually plug my y's back in. Y equals vx, way back up here at the beginning. But before I do that, I think I'll get rid of the ln's. What am I going to do with this minus sign right here? Minus sign.
Inside.
Take it over here.
Can you just,
No, it's just
Negative power.
negative of the subset.
All right, so I could take this minus sign here and bring it up here and it would become a power. But remember that eventually I'm going to want to get rid of v and plug my y's back in and get the y all by itself. I think I'd much rather take that minus sign and put it over here and have an x to the negative 1 so that I don't have an extra power over here that I have to mess with to try to get my y all by itself. Again, neither way is wrong. I'm just thinking ahead and thinking of the work I'm going to have to do. It's more convenient to have the minus sign over here. So I'm going to put the minus sign over here, minus ln x plus c equals ln absolute value 1 minus v squared. And then I do e on both sides. Well, the right-hand side is very easy. When I do e, I get 1 minus v squared. How about the left-hand side? Well, you just told me that this negative 1, what's it going to do? It's going to go in and become a power, so I could put the negative 1 right here. And the e and the ln are going to cancel out. That's going to give me an x to the negative 1 times c. This is going to be cx to the negative 1. Because of our same trick that we do over and over again. Technically, we really have an e to the c, but the e to the c, we just call it c. There's that same little goofy trick that we do over and over again. All right, c x to the negative 1 equals 1 minus y squared over x squared. Because v, going way back up here, v is y over x. So I plug those back in. And again, that's a perfectly acceptable answer right there. But again, my guess is in the back of the book, they would take this whole equation and they would multiply everything by x squared just to get rid of those fractions. So my guess is the answer in the back of the book is cx equals x squared minus y squared. Questions on that?
If you had like when you're trying to describe if it's homogeneous or not, if you had like x squared and then y cubed over x, would that y cubed over x have the same power?
Excellent question. This question was if my original equation had something like x squared equals y cubed over x dx, or dy dx, I mean. Is that still homogeneous? And the answer is absolutely yes. This has degree 2. This would have degree 3 minus 1, which would be 2. That would still be homogeneous. Now, more importantly, this one's separable because I could multiply by the x and the dx and solve it very easily that way. But yes, if you have a division like that, that's considered homogeneous still. Or if you have something like this, square root of x squared plus y squared equals y dy dx. This one over here is degree 1. This one is degree 1 because you have a square and a square root. Those powers cancel each other out and make a 1. So this equation would also be homogeneous. This is degree 1. This is degree 1. That's degree 1. So it could be written that way too. Okay? Other questions?
Does this apply to trig functions?
Yeah, that's what I was thinking. Like, it was like sine x squared equals cosine y squared dy dx.
No, it does not apply to trig functions.
So you couldn't solve that?
What was your equation again?
Sine x squared equals cosine y squared.
Sine x squared equals cosine y squared dy dx.
Yeah.
Well, I would point out first that that equation is separable. However, I still can't solve it. Because I can't integrate that. If I had an x sitting out here, I could integrate it. I could do a u substitution. But I can't integrate that. I can't integrate the right-hand side either. So just because it's separable doesn't mean you can solve it. So we would need something else. Can't solve that with what we know.
So we'll never have a trig function in there?
You will never have trig functions involved in your homogeneous equations. That's correct. Well, the moral of the story is there's no one step here that's difficult, but what are there? Lots and lots of steps. So what have you learned about differential equations?
They're long.
Differential equations are a lot of work. Nothing, like I said, there's no single step. I mean, if I told you, well, yeah, we went through it. Cancel out x squared. That was easy. Distribute. That was easy. Move the 2v squared over. That was easy. But how easy is it to make one mistake anywhere along the way, and then it bombs the whole thing? And that can happen. So the other moral of the story is, I hate reading these problems. Because when you make a mistake on step one, I have to take your mistake and follow it all the way the rest of the way through and see if you made any more mistakes, and that's a real pain in the neck. So I really ask that when you take your test, you get this problem right. Yes, that's a lot easier for me.
It's a lot easier if you just say, okay.
Just assume it's right, just close my eyes and give it a 10.